Question 4. A student carried out an experiment to find the temperature rise for a reaction between hydrochloric acid and sodium hydroxide. Used a measuring cylinder to place 50 centimetre cube of 0.4 mole decimetre cubed hydrochloric acid into a glass beaker. So if we wanted to, we could find out the number of grams there, we could find out the mass by using, we could work out the number of moles and the mass. So moles equals, concentration equals moles divided by volume, and then we could use the MR to work out the mass of hydrochloric acid if we needed to. The student recorded the temperature at 1 minute intervals for 3 minutes. At the 4th minute, they mixed the chemicals together and started to mix the solutions, didn't record the temperature. So we're going to have to extrapolate this line forward, and we're going to have to draw all these and extrapolate it back. So draw it back, and draw this one forward, draw this one back, look where it crosses the point at 4 minutes and measure the temperature change. Because we haven't got the temperature change at the 4th minute when we started mixing, we have to draw these lines forward and draw it back, a process called extrapolation. The student recorded the temperature at 1 minute intervals for a further 8 minutes. Fine, the results are shown, so we're going to have to draw it. Plot a graph of temperature up the side against time along the bottom. Use your graph to find the temperature rise at the 4th minute. Shows your working. So we've got the temperature up the y-axis using sensible scales. So we've got the temperature along the y-axis here going up the side, and we've got the time along the bottom. And then at the 4th minute, we're going to have to plot all the graph points correctly, all the points correctly on the graph. 2 lines are best fit, so one going forward and one coming backwards. Extrapolate to the 4th minute, so draw a line up from the 4th minute and see where the first line crosses and where the second line coming backwards crosses, and then measure the temperature change. And the temperature change should be around 2.1 degrees C if you've done that correctly. The uncertainty of each temperature, the key word here is each temperature reading, so you're measuring the temperature twice. For the thermometer using the experiment was 0.1. So you've got a temperature change of 2.1, but you've taken the temperature readings twice. So we need 2 times 0.1 because the uncertainty each time is 0.1, and we're taking 2 readings. So 0.2, 2 times 0.1 for the 2 readings. 0.2 out, it could be 0.2 plus or minus 0.2 out from the real value, divided by the temperature change, which is 2.1, multiplied by 100%. We've got a 9.5% uncertainty. Suggest a change to the experiment and minimise heat loss. Then you'd use an insulated cup or an insulated beaker, or maybe put a lid on it to reduce heat loss. Suggest and explain another change to the temperature that increased the percentage uncertainty in the use of the same thermometer. Well, look at the temperature change. It's only 2.1. So as you get a larger temperature change here, a larger temperature change, 0.2 divided by a larger number will give you a lower percentage reading. In the same as if you do a titration, if you use a small volume from your burette, you get a high percentage error. So you dilute your solutions in your burette. In this case, I want a larger temperature change, and so to get a larger temperature change, I'm going to increase the concentrations of my chemicals to try and increase the temperature change, increase the size of the temperature change, because if I get larger than 2.1 here, the larger this value, 0.2 divided by a larger value is going to give me a smaller percentage error. And you can do that by increasing the concentrations of the chemicals that you're using.